Hello, welcome to Pluralsight and to this course on Linux systems programming. I'm Dr. Chris Brown and this module is called Mastering Signals. Let me begin by answering the obvious question, what is a signal? Well, a signal represents some sort of an event that's delivered to a process by the kernel. The signal serves as notification that something has happened, usually something external to the process, that the process may want to respond to. A process chooses what it wants to do when a signal arrives by providing a function called a signal handler and then installing the handler. Now, if you're coming from a .NET background, you may be tempted to compare signals with the .NET events that drive the operation of, say, a Windows Forms application, and to liken signal handlers to .NET event handlers. But don't push the analogy very far, because the .NET events are much more fine-grained. There are vastly more different event types than there are signal types. And whilst the arrival of an event in a .NET program tends to be, on the whole, good news, signals in Linux are more likely to be bad news. So in this module, we'll start by looking at some of the common signal types and their typical uses. We'll see how to raise our own signals programmatically, and we'll see how to write and install our own signal handlers. And to finish, I'll suggest 7 useful things to do with signals. Now, there are a number of different signal types, and from the command line, the command kill-l will show all of them. You'll see that each one has a name and a number. Now, the higher numbered signals, the ones I've greyed out here, are the so-called POSIX real-time signals, and we certainly shan't be considering those. And even amongst the remainder, there's only maybe 6 or 8 that are likely to enter the consciousness of the average Linux systems programmer, so let's home in on these. Starting with signal number 1, the SIG-HUP signal, the hang-up signal. This has an interesting history. Many years ago, people would log into their Unix boxes using modems and dial-up lines. And there was a situation which we wanted to avoid, which was where the user simply disconnected, in other words, hung up the phone without logging out. And the danger was that the next user who connected on the same line would find themselves talking to the previous user's shell. And to prevent that happening, the modem hardware and the device driver would conspire together to send a SIG-HUP process to the shell when the user hung up the connection. Now, modems are largely history these days, but the SIG-HUP signal has found a sort of retirement job. It's interpreted by some daemons to mean go and reread your configuration file. SIGINT, the interrupt signal, is sent when you type a Control-C on your terminal. It's sent to the foreground process. SIGTRAP is a little more specialised. This is used if you're tracing or debugging a program, setting breakpoints and so on. SIG-FPE stands for floating point exception. That's a more self-inflicted signal. It occurs on certain types of arithmetic error, most commonly division by 0. Then we have the infamous SIG-KILL, signal number 9. You cannot catch or ignore a SIG-KILL signal, so it's lethal. If you receive a signal number 9, it's certain death. SIG-SEGV stands for segmentation violation, another self-inflicted signal. This will occur if the program attempts to access a memory address that's outside of its address space. This, of course, is a sure sign that there's a bug in the code. SIG-ALARM is part of the alarm clock mechanism in Linux. You can ask for a SIG-ALARM to be delivered to you after a certain amount of time has expired. SIGTERM is typically used as a polite please clean up and terminate signal, and it's sent, for example, in the early stages of shutting Linux down. It's sent to all the running processes. Finally, SIGCHILD is sent by a child process to its parent when the child process terminates. Now you'll see here in the column labelled default action, you'll see that in most cases it says term. That means that if you don't install a signal handler, the action will be to terminate the process. Those marked core also indicate that the default action is to terminate the process, but in addition it will write a core file, that is to say a memory image of the process at the time. And a few signals, such as sigchild in our table there, are ignored by default, so if you don't install a handler for them and one arrives, nothing happens. Now, as you'll have seen looking through that list, signals come from a whole variety of places. Some of them come from the terminal driver. Some of them originate in the hardware, such as the memory management unit. The command line tool kill can send any type of signal. Some of them originate within the kernel itself. But it's important to remember that wherever the signal originates, it's the kernel that delivers it to the process and forces control into the signal handler if one has been installed for that signal type. Okay, well, let's get a little nearer the code and look at some system calls. You can send a signal from within a program using the system call kill. The first argument is the target process ID, and the second argument is the number of the signal that you want to send. This can be either just a constant or a symbolic constant such as sigterm. Kill will return 0 on success and -1 on error. And there's a little trick that you can use. If you send a signal number of 0, it won't actually send a signal, it will merely test to see whether the target process actually exists. There are some rules, of course. You can only send a signal to a process if your real or effective user ID matches the user ID of the target. Be careful, by the way, notice the order of the arguments. The first one is the process ID, the second one is a signal number. Whereas in the command line tool of the same name, the first argument is the signal number and the second one is the process ID. Let me also mention raise, a system call that you can use to send yourself a signal. That's occasionally useful. Now, as I mentioned earlier, the default action of most signals is to terminate the process. And when this happens, the process doesn't return an exit code in the usual way. Instead, the lower 7 bits of the status contains the number of the signal that caused the process to terminate. Then there's a bit that says whether a core dump was written, and the upper byte, where the exit code usually goes, will be 0. Now, we looked at this before in Module 5. There are some macros, which I've shown here, that make it easy for a parent process that's just waited for one of its children to figure out if the child was terminated by a signal, and if so, which one.